So this is a continuation of a series of videos on arithmetic of set theory. In the first one, we showed the analogy between arithmetic of natural numbers and arithmetic of sets. One of the important things we mentioned that we're going to explicitly use in this video is how we how we encode rather, natural numbers as sets, and that's given by the rule of representing every natural number as a set of all the numbers that are strictly less than that number, with the starting number 0 being represented as the empty set. Now let us look at some examples of set theoretic expressions that we could evaluate as similarly to how we evaluate arithmetic expressions with natural numbers. So let's look at the following one. 2 union with 3 multiplied by 4. So let's evaluate this expression as an expression of sets. So to do that, we would want to expand each of the numbers as sets to make it clear what their elements are, so we can then decide without less chance of an error what the resulting result of the operations will be, right? So number 2 is the set 0, 1, right? And we're supposed to take the union of that with the number 3, which is the set 0, 1, 2. And then we're supposed to take the Cartesian product of that set with the set of all numbers from 0 to 4. So that's 0, 1, 2, and 3. Okay, so the union of these two sets, because 0 and 1 is actually also found in the other one, is going to be the set 0, 1, 2. So we end up taking the Cartesian product of this set with this set. And now to form that product, what we have to do is to take the set of all ordered pairs. So that will be 0, 0, 0, 1, 0, 2, 0, 3, then 1, 0, and so on, right? So we're going to list all combinations, 2, 0, and so on. And if we follow listing elements in this specific order, the last one is going to be 2, 3. How many are there going to be in total? Well, 3 elements are being paired with 4 elements, so it's going to be 3 times 4 elements. So here we're going to get a set having 3 times 4 elements. We don't have a specific representation for a set like this. We just have to list its elements. That's the only way we can write it out. We could write it out in a little bit more economical way using arithmetic of natural numbers. We could say that it's the set of all ordered pairs A, B, where A is less or equal to 2 and B is less or equal to 3. And we also have to say that the A and the B are both natural numbers. But now, if we write it like this, we are a bit disobeying traditions here, because these two sets being elements of a set of natural numbers, first of all means that we are now really declaring that the natural numbers must be sets defined this way, and we only adopted this as a notation, not as a formal definition of a natural number. And secondly, we are now forcing this set to be part of the universe, because we are using the element symbol for it. And then thirdly, we now are understanding the less or equal relation the way less or equal works for natural numbers. So this notation builds on various agreements and definitions which we haven't yet made. So it is not actually a good idea to use it because of that. But one could if one would introduce all these definitions and notation, then one could write things out like this in a short way. So that's one example of evaluating an expression from arithmetic of sets. Let's look at another example. I'm going to remove all the calculations and just leave the expression we worked with, not to forget what our initial example was. Not that we're going to use it, just for the record. So that was one example. Now let's look at another example, something like one thing that we actually forgot to mention in the previous video is the idea of power set. So let's incorporate this here. Power set of 2 intersected with one Cartesian product with 2. So let's try to evaluate this expression. Well, first let's expand what 2 is. 2 is the set whose elements is 0 and 1. I should rather say whose elements are 0 and 1. And well, let's also expand 1 and 2. So 1 is this set, and 2 is this set, right? Now we can expand this further. So the power set of the set of having 0 and 1 as its elements is going to have 4 elements because it's all possible subsets of the set. So one of the subsets is the empty set, but we denote empty set as 0, so we can put 0 there. And then we've got singletons containing 0 and singleton of 1. And then we've got the entire set. So these are all possible subsets of the 0, 1 set. Now that has to be intersected with this Cartesian product. Because one of these sets has only one element, the Cartesian product also will have only one element. That will be the ordered pair, the unique element of, I actually said what I said is wrong. The Cartesian product is going to have as many elements as the other set has. And that's because the same 0 is now being paired with 2 different elements of the other set, which are 0 and 1. So at this point, we've computed the power set, and we've also computed the Cartesian product. Let's continue on with the calculation. Now what we want to do is to intersect these sets. But to do that, we have to be careful because just like this, looking at this, we might think, okay, there's nothing in common, but we have to remind ourselves that the ordered pairs are themselves defined as sets, right? So, and what if one of those sets ends up matching with one of the elements listed on the left-hand side? So that will be relevant for the intersection because intersection picks out the common elements. So let's expand this further. The ordered pair 0, 0 is going to be, by the definition of ordered pair, this set. So let me remind you that. So for general A and B, the ordered pair is defined as the set of singleton A and the set AB. Now when A is equal to B, in that case, this becomes set A, so altogether it becomes this, which is what I used here. So that's the ordered pair 0, 0, and by the same definition in the general case, because here the components are different, we're going to get this set. So that's a 1 here. Okay, now we have to intersect these sets, and to do that we'll have to look for common elements of them. And again, we have to be careful in terms of what the numbers seen as sets stand for. So this is the empty set, right? And clearly on this side we don't have any empty sets, so 0 is not going to fall in the intersection. What about this one? Well, this one is a singleton of the empty set, right? Do we have the singleton of the empty set on this side, either here or there? Well, if we look at these sets, of course 0 is still the empty set there, but there are extra brackets in here, and in there is even one that destroys the possibility of that being the same as that. Now I see that I should have had another bracket here. Um, so this element cannot be found in this set. So it's not going to be included in the intersection. We can, to ease us with the computation, we can maybe mark those elements which we've checked are not going to fall in the intersection. We could now go on with this argument. Let's see. So now let's look at the singleton of 1. Remember, 1 is defined as singleton of 0. So it's actually that set, singleton of the empty set. And therefore, the singleton of 1 is going to be this set. And that's exactly what we see here, right? So this is actually the same as that, because 0 is the empty set. So, so it turns out that this element in the left-hand side set can also be found on the right-hand side. So that's going to be included in the intersection. So we can write it down. Now the last one is this one, and we have to check for that. So again, let's expand it and see what it expands to check whether it can be found on the right-hand side or not. So this is going to expand to the empty set, because 0 is empty set and 1 is a singleton of the empty set. And this set is neither equal to that nor it's equal to the other one. Why isn't it equal to the other one? Because this set has an empty set as an element, and the other one does not have empty set as its element. It only has a singleton empty set as its element, which is not the same as the empty set. So therefore, although this one was found in the intersection, the other one, and namely this one, also falls out from the intersection. So in the end, the intersection only contains that one element, and so that's the intersection. Great. So these are the two examples which illustrate how arithmetic can be performed on sets. And that's it for this video.